Thank you very much, Andrea. It's a pleasure to be an advisor to this group, as well as other European groups in the past, and a pleasure to deal with all of you. I enjoyed the presentations in March from the students trying to say what they're going to work on, and this week, the progress they have made. As for me, yes, I want to highlight my European roots. I was actually born in Greece, finished my high school in Greece, and then immigrated to Canada, went to the University of Manitoba here in Winnipeg, and then did some graduate work at the University of Alberta in Edmonton. And I have been dealing with environmental issues, especially fish and fisheries related issues, practically all my career, over 40 years, 45 years or so. And the challenging thing for me was, back when I started, the word ecohydraulics didn't exist. It was coined later on in the 90s and so on. But we were doing ecohydraulic work right from the start. The difficulty was that we were better on the hydrodynamic side. We didn't have as much quantitative information on the biological side, but eventually that came along too, because the tools were developed to get us there. And I was one of the happiest people to see that. And I'm very happy to see the explosion, essentially, of work in this ecohydraulic area over the last number of decades. And it's, if anything, it's accelerating, which is wonderful to see. We even have our own journal nowadays. Okay, so turbulent flow is a very normal condition, actually, for a lot of fish, especially those that seem to be migrating. I'm trying to change. Okay, here we go. So you can see here on the pictures a variety of rivers primarily and streams that can present challenges to fish that are migrating upstream or downstream for that matter. And that's a normal condition, biological requirement for a lot of species, not just salmon, but many, many species. And it's more or less a normal condition for all these fish. And we call them rheophilic because they love the flowing water, essentially. That's what the Greek term rheophilic means. But there's some challenges too, whether they're natural or artificial, because people, for example, have interfered with their movements or their habitats, and that presents very many challenges. One of which is the upper right picture that you see here. Actually, there was a natural canyon in Fraser River in British Columbia, which was difficult enough for salmon primarily to move through, but they were making it. But back about more than a century ago, a railway was being built from west to east across Canada, and a landslide occurred there. The canyon became much more narrow. You can see how turbulent the flow and how fast it is there. And these structures that you see here are actually fishways to help salmon. And they took a few decades and a collaboration between Americans and Canadians, engineers and biologists, to develop them. And that's the famous vertical slot design that people have adopted for many other species. But going back to where I first started in this, we were doing, in Canada, we were building some highways up north in the Northwest Territories. And here's a challenge for fish. You know, crossing streams with culverts was a common enough method. Trying to save money, you squeeze the culvert to be the smallest possible, for example, but you can see, especially at low flows, that there's lots of water there and turbulence, even some steps that fish have to jump over if they needed to go in. And the first study that I was involved was a field study, and it actually was set in motion before I arrived at the scene. And you know, the idea was, can we put something within this culvert and this culvert called baffles, different veins at the bottom, to slow down the velocity to get them through. But you can see at very low flows also, it's still a challenge for fish to get in. This culvert was left plain, no. And that was our first study that we published in a technical report back in '78. But the interesting thing was that this crossing has become of interest lately because there's a law in Canada that says if you affect fish habitat, you have to compensate for it. And a lot of new developers, for example, including diamond mines in Northwest Territories, some of the first diamond mines in Canada, pick this as an alternative. If you fix the habitat here, you're compensating for some other habitat that you lost through your project developing a diamond mine. And I was involved as a consultant this time with another consulting company to find out how could you actually do it. And essentially we said, for this size river, these flows and the abilities of these fish, the best way is to replace it with a bridge. And even back then, I was suspecting that that might have been the case back in the 70s when I first started. The next highway built was, again, at the beginning of my career, was what we call the Liard Highway, again in the Northwest Territories. And back then, there was, like I say, very little information on fish. In this region, we had very little information even on hydrology or morphology or anything you might want to design a highway and stream crossings for that matter. So this is where we came up with the idea of stream simulation. Essentially, you take the culvert, wrap the stream around it, put heavier riprap than you normally probably find. Just to being engineers and being conservative, we would like to make sure that those stones stay in there to benefit reduction in velocity and benefit fish migrations. And actually, there was a follow-up study by biologists at the Freshwater Institute, where I was working at the time, to show that yes, fish had no problem moving through, and actually it was easy for them to get through. Nowadays, what that kind of idea we might call nature-like fishways, or even nature-based solutions in a more broad way. And here is an example, much more recent example, which is under construction now in the Netherlands. It's called Fish Migration River. And essentially, these are the openings for fish to come through here. Actually, there is a vertical slot fishway in there, and then through here to get into this lake. Because the Dutch decided to, this was a very old dike that protects the lowland areas from the sea, and they are replacing that to accommodate much bigger boats and much more traffic but these days they had to also meet much better environmental standards, and the fish that are involved are there. And we had a hand in this, but that's what you would call nowadays more or less nature-based solutions. But there's still turbulent flow in most of these places that fish have to negotiate through. So I want to take you back to some simple ideas, because this principle of similarity has turned out to be a very powerful tool, not only for geometry, but for hydrodynamics, and you'll see also for biology and ecology. So if we go back to ancient Greece, essentially, and Euclidean geometry, if you just take some generalizations that you can make for similarity between shapes. So for example, all circles are similar, just the size changes. So they have a very special property. That means that, which we actually define as pi, a special number. The circumference divided by the diameter is a fixed number for all circles. Of course, similarity doesn't mean only for the circle. It could be squares, it could be rectangles, it could be whatever you like, as long as you expand. So essentially, that leads us to scaling laws. Another special number that found you can find examples in art as well as in biology, is the so-called golden ratio. The golden ratio really starts with a rectangle. It's a special rectangle that if you remove a square out of it, you end up with a rectangle, which is also similar to the original rectangle. And that has been called the golden ratio, because the rectangle, the sides of the rectangle, that ratio is there. And there's a famous equation there that I have on the. And in terms of art, if you take the bottom here in the middle and you connect the square corners and you keep on going around as you make the rectangle smaller, you end up with this kind of shape, which you find in Nautilus, the biological shape, this animal. And in terms of art, the Parthenon, supposedly Phidias, who was the architect then, actually designed a lot of these dimensions on the rectangles using the golden ratio. But essentially what we're saying is if you take areas of circles or squares or something, there's the power of 2 is the exponent where you have to do it, and they're all similar. If you go to volumes, then the power of 3 comes in. And can we extend that to say hydrodynamics? Lots of people have done that in many hydrodynamic phenomena. I'm giving you one from my graduate work, actually. We were the first ones to apply it on fishways and fishway flows. This is a channel, which is a type of a Denil fishway. They call it steep pass because of a modern adaptation of it and its use mostly in Alaska to begin with, but it's also used in the east coast of Canada and the US for a bit still today. And the turbulence there is terrific. But there's a certain kind of turbulence but it has been used by a lot of fish. And I'm giving you here how the velocity profile changes. For the first time we found out back, we're talking the 80s now, how the velocity profile is similar by just taking the maximum value of the velocity in its profile. And this is the depth along up to the water surface, and the D is the total depth, Y is the points along the column. So if you divide that with the actual velocity at any point you wish, divided by the maximum velocity, you have a plot that all the points come together. So there's many applications on this, and the similarity has been used in anything from ocean to atmospheric circulation, for climate change modeling, for example, fluid mechanics. Even the molten interior of the Earth is essentially a fluid, and the tectonic plates float on it. And in aerodynamics, you can think of airplanes and their shapes and so on, and how they make them more efficient. Hydrodynamics, of course. And Snyder in 2009 gives you a lot of examples, not only from hydrodynamics, but from biology and ecology, which to me is even more interesting, that the principle of similarity applies there as well. So for example, you can see here on the right, a graph, which shows how a fish or many other animals can change their mass as they grow. But going back to the geometry, the scaling, we said if it was length to volume, it would be the 1/3, right? Exponent length to volume. And if it was surface, like a square surface or a sphere or a round surface, circle, it would be the volume to the 2/3. You can reverse instead of going volume to surface squared, you'd say surface is 2/3 of the volume, right? So a 2/3 exponent for scaling seems to be pretty amazingly close as a first approximation, if you like, with a lot of these organisms, from tiny ones to fish, to rats, to hen, to cows, to pigs, and so on, that West and Thor have put together. And they found, and other biological studies found, that actually the exponent is 3/4 as opposed to 2/3. So only 1/12 difference as a first approximation. So the 1/3 as a first approximation is not very bad at all. It's pretty good as a first approximation. And this has been found, and it's called allometry. It started as allometry, but the concept of allometry has been expanded to more than just shape and growth with time. And this can now include not only morphology and body parts, but physiological, more importantly, which relates to fish and swimming abilities and moving through water and so on. Physiological aspects and metabolic rate, for example, could be a representative of that, as well as ecological aspects, right? The wingspan of a bird versus the flight performance, they're related, and there is some similarity among birds and so on. So physiological variables such as heart and the respiratory rates, and blood circulation, which you can think of, a fish would need to physiologically move through water, would need to utilize some of these aspects, are typically also scaling with multiples of 1/4. So a lot of studies on swimming performance do not actually include physiology in it, or this allometric scaling. Yet, I think there is one study, which I'll highlight a little bit more later too, that did consider allometry, how the shape of the fish might be in fact affecting their performance. But let's go back to a bit more fundamental hydrodynamics, because we have ways to classify flows as laminar or turbulent. And this is reflected essentially in what we call the Reynolds number, which is really a ratio of inertial forces to viscous forces. So you can see the expression there. It depends on the velocity and some length, characteristic length. And depending on whether the Reynolds number is very low, you could have the laminar, very straight kind of flow. And when it's higher, it's what we call turbulent flow. So if you can think of a fish swimming in different areas, and the size of that fish could be represented by the L characteristic length. So you right away, you can see that the longer the fish, the higher the Reynolds number could be. And as well as the velocity or the speed of the fish is able to generate, the faster fish would generate higher Reynolds number than smaller fish. In terms of water properties, kinematic viscosity and dynamic viscosity, they change very little with temperature primarily. So the velocity, the speed of the fish and the length of the fish are the main variables that change whether these fish are moving in viscous or inertial sublayers. And essentially, viscosity causes some sort of a resistance, right, to flow as fish move through water. And essentially, fish drag along as they move a layer of water, think of it that way, along their body as they swim. So this boundary layer of this layer of water that they drag along is thicker for smaller and slower fish, which means lower Reynolds number, and larger and faster fish, higher Reynolds number. In more hydrodynamic, more physical relationships, you actually can quantify this, and you can see there is a difference on this drag force that is applied by the fish. Let's say in this case it's a sphere, and the surface of the sphere can make a difference as to how it relates to the Reynolds number. A smooth, you can see a different curve for a smooth one versus a rough one. So the same thing for fish, because they have adapted to moving through water efficiently, they're not exactly smooth, their surface, but a lot of them know how to cope almost like a smooth kind of a boundary, because they have adapted to it and they have ways to minimize the resistance of the flow. So here's a way that physics people can put something together in a more recent look at this. And you can see there's tremendous scales of Reynolds number from 2 to 9 or 10, right? Orders of magnitude. So depending on what you're looking at in terms of an animal that swims through water, the Reynolds number could be dramatically different. But there's some commonality and similarity as to how fish swim through these different flows. And this is sort of summarizing that essentially. And there's the tail beat frequency is involved, the length of the fish is involved, of course the speed of the fish is involved, as well as the resisting forces and the thrust. The fish itself is pushing through water, but that's much more of a physiological process than the hydrodynamic one. So you can analyze the hydrodynamics this way, but it does not include any physiological variables. For example, if you had how long a fish can last, can endure through a flow, maybe that will give you an indication of physiological limitations on the fish. Here, these authors were able to put it together and show you how laminar flow and turbulent flow may be affecting things and where fish might land, which is a very good way to organize and understand the flow conditions and how they may relate to fish movement through water. It's a broad trend type of analysis, and you can see that scaling ratios and dimensionless parameters come into play beyond Reynolds number, this so-called swimming number that they came up with. Now, another very important number that the dimensions number that is important for hydrodynamics, but it turns out to be also important for fish movements, is what we call the fruit number. The fruit number is a ratio of inertial forces to gravitational forces. And traditionally, that ratio is expressed actually as the square root of that ratio. And most of the time that you see a fruit number is expressed as the speed of water, or a fish in this case, divided by the square root of gravity and the length of the fish in that case. There's one more adaptation, if you like, to the fruit number called the densimetric fruit number. And that is very helpful when you have an object which is a different density than water. Let's say a fish, if it's exactly the same density as water, it doesn't matter, it reduces to the same thing. But if there is a different density, this fruit number expressed this way takes that into account. Essentially has to do with the density of the fish versus the density of the water. Or in this case, if we're looking at the submarine, is another way to illustrate how a fish might be more closer to a submarine than a water surface, a phenomena of supercritical and subcritical flows that we can separate from using the fruit number. But in that case, the fruit number is defined with velocity of the water and the depth of the water. When we're talking about a submarine or a fish, we're talking about velocity of the submarine, or the speed of the submarine or the fish, and the length of the submarine or the fish. And here's a sort of an illustration of how even a submarine, even if it's below surface, it will create waves, different waves that also affect motion through the water. And especially in shallower waters and shallower diving depths, the velocity increases can be significant and influenced by the fruit number as well. So the fruit number can be an important parameter for swimming the fish as well. So how do we measure how fish swim, especially in laminar or in turbulent flow? And laminar is very hard to generate, actually, because most of the time we have turbulent flow as the most representative. And then also, not only how we measure it, but do we have many measurements on these fish? And it turns out that maybe we have some idea of speeds of fish on about less than 1% of all the species that exist on our planet. So there's a great need to collect more data. How do we do it more better might be the good question. And at the same time, we need to utilize what we have in a more full way, in a more general way, if you like. So if nothing else, at least we can take educational guesses if we have to design things rather than no information to go by. So can we examine this kind of data sets and establish some trends, which can lead us to some practical applications, essentially, is what we are talking about. Now, the different methods, whether it's the swim chamber over here, which is more like a treadmill in human terms, or what we call ecohydraulic flumes these days. And some of these were done some time ago, but we adapted it. For example, we were the first ones to adapt it to modern technology. You can put tags on fish and follow them. And this one was the first one we did in a temporary flume in Newfoundland back in '96. And Atlantic salmon would come up the stream, go in on their own volitionally. We tagged them. And then that way we could, we have antennas all along here. We were able to detect where they were at what time and what distance they covered. And of course, we could fix whatever velocities. And this was representative because it's essentially turbulent flow in an open channel. We also developed a mobile flume, which you can move around and test fish that way. Most of the data turns out to be from the swimming chambers, but a lot more data from these ecohydraulic flumes more recently have been generated. And each method has limitations, and exactly what it measures is worth in looking into more critically, and whether it affects the fish because this is an artificial environment, especially these swimming chambers. Or if you transfer fish from this one on the right was actually on a hatchery. So is it wild fish? Is it hatchery fish? Is it even on these volitional ones, can we measure everything precisely to the point where we can actually analyze the situation very precisely? But at least we can set up some trends. So what we have done is there a way to look at that data in at least overall view? So the other thing that comes in is what we call, and this comes mostly from the biological literature, swimming modes. And you can classify actually different species by how they swim through water. So for example, an eel uses most of its body to thrust through, and they need actually a lot of times a rougher surface to move through. While what we call a subcarangiform, that's what's called classically an anguilliform swimming mode, and there's certain properties that you can associate with them in terms of wavelength and tail beat amplitude and clear width that they need to swim through. And typical fish for that would be eel, lamprey, and burbot, for example. There are others. Subcarangiform is a very interesting category because it includes quite a number of species. You can see salmonids are here, rheophilic cyprinids are here, many cyprinids, as well as persids and others that use this type of form. And it's characteristic. It doesn't use the entire length of the body to go through, but usually about a half to 1/3 of the body. And then there's sort of a subcategory, I would say, carangiform. It's slightly different than subcarangiform because the body undulations are a little longer than the subcarangiform normally. And then there's things like tuna and so on that completely use very little of just the tail primarily to move through water. And then there's put sturgeon in a special category because it formally has not been classified as one of the other groups, and they do use different modes, and their swimming performance seems to be different than many other species as well. So back in the early 90s, I was trying to come up with data that might help with fishway design. So swimming speed was one of the things. So I searched through literature and I was able to use this classification of swimming modes to put together at least enough data for two categories, the subcarangiform and the anguilliform. And in the anguilliform, I found two different species. And in the subcarangiform, I had about 18 different species. And what I was trying to do is say, okay, let's call this the fruit number. You can remember what I was talking a moment ago about a fruit number for fish. That's the speed of the fish. That's gravity, gravitational acceleration, and the length of the fish, L, right? Sorry. And then on the x-axis, I came up with some sort of idea of how long could they endure this, the time element of endurance or fatigue sometimes. And most of this data came from two different tests, mostly from swimming chambers, because at that time, open channels and ecohydraulic channels were not available. We started them shortly after. But you can see here that there's a good correlation actually for that many species in those two swimming modes. Overall trends, yes, there's a lot of scatter around it, and it gives you, the time elements we looked at, endurances of 1 second to 30 minutes, and the fish lengths that we represented in that data set. Another group in New Zealand that Vladimir Nikora was part of it. I think he was a student, PhD student maybe at the time when he was in New Zealand. He came up with these are a similar kind of an idea, but different. So the fruit number is here again, but they use the actual ratio of the two forces as opposed to the square root. So essentially, this number over here is the square of the number I was using. And in terms of x-axis, you have the Reynolds number here. Actually, it's represented here. And this parameter, which includes time to fatigue, gravity, and swimming speed of fish. And they found a very good correlation too. Again, they're scattered around it and so on, and it's one species. But again, dimensionless parameters, fruit number, Reynolds number, type of parameters, were able to bring a lot of these data together and give us some sort of generalized result, which we could use potentially for trends. Now, what we did more recently, and actually before I left the Freshwater Institute, we started to update the database that I started with back here. And in 2016, we published a report which was very reviewed by a number of experts, and we had interaction. It was part of the Government of Canada, Department of Fisheries and Oceans, and they have a very thorough review of those aspects. And it's actually available online. But I just want to highlight a few things that we found. Essentially, it reinforced the analysis that I had done earlier, but a lot more species and a lot more data were involved in this time. Just to give you an idea of what happens when you actually try to group it, I'll stick to just the fruit number for fish here. And very many classical studies with fish actually use body lengths per second as sort of a measure of the speed of the fish, which is fine, except that I would love them to report not only body lengths per second, but actually give you the length of the fish for each data set, because then you can manipulate the data in other ways if that's what you wish to do, instead of reporting just body lengths without the per second rather than without the length in it. So if you take a single species like the steelhead trout from the literature again, and you regress it with in terms of the time element that I was mentioning, you can see that there is a certain R² associated with that one species when you use the body lengths per second option, which is really speed divided by length, versus the fruit number, fish fruit number equivalent. So the R² is much higher when you use the U² than when you use the U over L. Now, if you look at these two species, steelhead and rainbow trout actually are the same species. One, the rainbow trout is freshwater, the steelhead is the anadromous version of the same thing. So if you add to the steelhead trout data, the rainbow trout data, this is the R² you get with body lengths per second and a fairly high number for U star. Now, add one more species, one group of species actually. All the Pacific salmon are represented by this Oncorhynchus. R² is still going up, R² is still very high with U star. And if you add one more, the trout, the different trout, most of them are freshwater trout, then you still have a very good correlation with, especially with R², much higher than this. And there's difficulties and challenges even with this data set, because, for example, most of this is average values of burst and prolonged speeds. Even the length of the fish is an average of some sort within plus or minus 10% because we had to group them. And the length of the fish is not very precisely reported all the time. Sometimes it's fork length, it's not consistent, I should say. It's precisely measured, but not consistent. Sometimes it's only fork length that it's reported. Sometimes it's total length. Sometimes it's standard length. But when you're calling it a length, the precision, some of the precision is lost if you're using them together, right? So this dimensionless fish speed essentially, which includes the square root of length, provides much higher regressions than the traditional body lengths per second parameter. And it's illustrated here with that same group of species. You can see all the points. It's the same points on both graphs. The R-square is much higher, and you can see all the species here that are involved in these data sets. And here's the big difference between sort of body lengths per second and using the fish fruit number. When you use body lengths per second, essentially, the small fish separate from the large fish because the length is still playing a big role. But when you use this U star, small fish and large fish start coming together, whether it's the large steelhead here or the small brook trout here. They seem to come very close together, steelhead and the brook trout. And then the same, the brook trout here. Then the same thing, actually, it's a barbel, completely different species, though not a salmonid. It's close to here again. Nace, another cyprinid, over here. So these different data sets come together in a more powerful way when you're using the dimensionless fruit number. Here's another way to look at it. Using sturgeon, this is limited because it's only juveniles we're talking about, but essentially the blue line is the absolute speed, meters per second. And of course, this meters per second, the speed of larger fish, longer fish is higher than smaller fish. And when you use relative body lengths per second relative speed, here's the classical line. It reduces as fish get longer. But when you use the fruit number, it's almost like a constant. You can almost put a constant value through it. Now, is there any evidence that any of this stuff relates to the field and actually is close to what we can come up from field studies? Here's a natural barrier in Alaska. And I had I was fortunate to visit that as well as many other sites when I first started, because my objective was to find out what other people knew from the East Coast and the West Coast. Everybody was studying salmon. Nobody was studying freshwater species at the time, but I tried to learn as much as possible from others and then see if we can apply it elsewhere. So here's a natural rapids that salmon would come up to here and couldn't make it up. So the Alaskans decided to, at the same time, they were trying to develop some sort of a unit of fishway that is easy to transport even by helicopter and plunk it into remote sites, since it's very hard to get the heavy equipment to construct anything in some of those sites. So they developed this idea of the steep pass, which is a Deniel fishway that we studied hydraulically. I showed you a little earlier. So they put these steep pass fishways here, and actually they have some pools in between, resting pools in between. This is what it looks like. That's the original. And then later on, a lot more salmon were going through, so they needed to increase the capacity. So they actually did this. They double it, more than double it. And at the same time, they were running some experiments. And for about 4 years, they had the longest fishway length, steep pass, that they were using was 60 meters long. And actually, they have observations that these sockeye salmon were going right through it. The slope of the fishways is about 22%. So we have a lot of data from that says fishways, salmon, sockeye salmon were right. The only thing we have from hydraulically is the depth of the water and the depth of the steep pass. And that's what we had replicated actually in the lab in one of my studies. And essentially, this was for 20% slope, not exactly 22, and pretty close to the full discharge that this fishway can take. And this is a velocity distribution in that steep pass fishway. And I highlighted with red anything that is above about 58 centimeters per second, okay? Which is sort of the velocity we're estimating another way that these fish should be able to do very well. So it turns out that these fish were about 520 millimeters long. The analysis that we updated the database and so on, we developed into a database and also extracted fish swimming abilities. And actually there's a website you can go to, and it gives you all the calculations, whether it's swimming distance versus water velocity, swimming time versus water velocity, or any combination of those variables. So estimating with margins, of course, and sometimes there are wide margins, is where this came from. So based on the swimming performance data from actual data, and then projecting to the analysis with a fruit number, the fish fruit number that I was talking about. And then you can put out what 95% of the fish can do this, 85% of the fish can do that, and so on. So according to this analysis, then, over 95% of the fish can do 58 centimeters per second, which is what we measured in the lab. So in Alaska, they found that they could go through 60 meters. Here, we're saying, yes, these predictions are reasonable at least. And to put things further into perspective and emphasize the fact that fish are great in their medium, because they're moving through water, they have adapted over the many centuries, and so they're really good at swimming through water, even though we don't always understand how they do it, and we can't always translate the hydrodynamics and the physiological aspects into our understanding. We're trying to make progress. So according to these curves, a 520 millimeter salmon, here is on this box at the bottom, would swim 100 meters at 3 meters per second for 10 seconds, and for 10 seconds, 7 meters per second. So let's compare that with an Olympic athlete in terms of swimming. 100 meters, the Olympics were held not too long ago. Freestyle swimming, around 50 seconds. Or 2 meters per second. So you can see how a fish can be much faster than a human in water. But then let's look at running. 100 meters for a human, an Olympic record is about 10 seconds or 10 meters per second. So that's pretty fast. The other way to look at it is a human is, let's say, an average of 1.8 meters tall. Let's consider that its length. 100 meters would be about 55 body lengths. But a 520 millimeter salmon for 100 meters would be 192 body lengths. And for 55 body lengths, this salmon would swim around 30 meters or just under 30 meters. So again, all that seems to come together, but to give you some reasonable, not the most accurate, but reasonable estimates. Of course, we can go into more detail on the turbulent flow aspects, and hydrodynamicists have studied this for a long time, and we understand it better now than a long time ago, but there's still a lot of questions left. But one way to classify all these aspects is through mean velocities and the fluctuation allowed the velocities, and we can look at those aspects and come up with turbulent kinetic energy as one of the variables that can characterize a turbulent flow, and that can be a horizontal component or a lateral component or a vertical component. And we can look at the shear stress that is generated by these differences in velocities and so on. And all that can actually translate into how they may be affecting fish as well and their movement through water. Then we can present fish with different regimes. And actually we do that whenever we build a fish passage facility, a fish way to help them go upstream or downstream. We actually present them with turbulent flow of different varieties. And we were able to classify at least two major varieties of flow. What we call a plunging flow and what we call a streaming flow. In the plunging flow, actually the water from a pool to a pool goes straight down and turns around in here and then continues over. In a plunging flow, actually, there's a carryover from one pool to the next. It's like skimming on top of the surface and moving down. And it turns out that these types of flow may be affecting different species differently, because some of them may be okay with plunging flow, others may prefer streaming flow. So we're able to classify this through hydrodynamics. And when does this occur? When does streaming flow occur? When does plunging flow occur? So this is like a map, which depends on the distance between weirs, the weir height, and the layer of water that is moving on top of, and so on. And you can actually, again, with dimensionless numbers, you can estimate discharge, you can estimate the spaces between them and the height, and classify the flow into plunging, the middle here, or streaming up here. And that help us say, okay, this fishway, if a fish like plunging flow, then how do we generate it? How far can we design these to make sure that it's always a plunging flow, or if we prefer streaming flow? Now, do we know if fish like one or the other? Here's a study with a cyprinet, a couple of cyprinets actually, and there are differences between them in terms of what they prefer, putting them in these flows. And essentially, in plunging flow, the bottom, these fishways also had an orifice, not just the flow was not only on top, they also had orifices where we tested the fish. So in plunging flow, the bottom orifice was strongly preferred by both species. So both of these species like to go under the water through the orifice rather than go over the weirs. In streaming flow, though, chub preferred to jump to go over the weirs more so than the barbel. So there are differences, and those are behavioral differences. Abilities probably are not much different unless the fish is much different length. As we said in the swimming performance, the longer fish will have better swimming performance. So this is behavioral, and we need to know that if we're going to be effective in designing these fishways. Another mode of operation might be that the fish actually moves up through the flow, or it jams. And it turns out that, of course, the pool below is important, and the depth of it, as well as what comes from here. And it's not as simple as you might think. It's not only dependent on the delta H here, the difference in elevation in head, in elevation between here and here. So there's a combination of the two that gives you the most effective way of these fish. And sometimes they would choose to move through this way. Sometimes they would actually jump. Now, it goes back to some time ago when the Columbia River is one of our best hydraulic labs in real life, actually, because people have done so many experiments over there and spent so much money that we have learned a lot. The only limitation is that we learn a lot about Pacific salmon and not many other species. There's one more species, though, that we learned quite a bit about from these dams. Okay, so I'm giving you some pictures here from the Columbia Dam, Columbia River, and the first dam that you see when you go from the ocean up is Bonneville. And as these were done or being built over the years, the design changed a little bit in terms of these are straight weirs, and they have orifices below as well. But then another design is what they call the ice harbor, which is actually splits the weir in two. They have this middle section here and two on the side here, and there's still, you can still see the orifices below. So the flow is a little different on the ice harbor than on the Bonneville type of. Now these are huge fishways, and that relates to schooling that some species like to move together as schools, others like to move individually, and it doesn't matter to them. So if you have a school of fish, actually, it turns out they need a lot more room to move through, not very narrow passages. So that could be a consideration. So what happened back in '68, this John Day Dam, which had this ice harbor type of design, they found out that American shad, and these are not native to the Columbia River. They were actually brought from the east coast of the US to the west coast, and they were introduced to the river. So these fish had no difficulty moving up some of the fishways, but when this John Day Dam was constructed, somehow they stopped moving at certain sections of these fishways, while the Pacific salmon, the rest of the species that were moving up, definitely moved up effectively, no problem. So what was the problem? They went back to the lab, and back then they had a nice lab on top of the Bonneville Fishway, for example, and they were able to move fish in from the fishway right into the lab, and they played around with this regulating section. It turns out to be, in order to regulate the flow through the fishway to create the proper conditions, plunging flow, they regulated the flow coming into the fishway with a section, more so than they did at Bonneville. And that seemed to become the problem. Fish were stopping there, and the American shad, they wouldn't move upstream. So they experimented, and they changed a couple of different variations that they looked at to see whether, and they tested American shad and salmon in the lab as well, to see whether they prefer something like this or a modification like this. This turns out to be more like a vertical slot, actually. So it turned out that in the lab, a lot more American shad preferred this option. So they went with this plan B and implemented it in the John Day Dam. First in the first ladder, and then in other ladders as well. So it turns out that, yeah, a lot more American shad were actually moving. Not 100%, but 73%, for example, while salmon, 94% of them were actually moving up through. Even suckers and northern schoolfish and common carp and other species were also moving up in good numbers. And since then, the American shad, which again, we're not a native species in this river, have dramatically increased in number to the point that there are sort of a lot more American shad than native salmon in the Columbia River. And that was because they changed the flow from plunging, it turns out, to more streaming type of conditions. Here's another study, interesting study, which was done through videography on the east coast of the US. This was another fishway that was built to generate plunging kind of conditions. Salmon, Atlantic salmon were involved in this one, but American shad were also involved. So Alex Harrow and Boyd Kennard, which are well known on the East Coast as well, and internationally for that matter, started to try to make observations. Why do these native, now here's their native habitat, American shad, we're not going through these Cabot fishway. Well, it turns out through the videography that they were stalling again because of the plunging flow, and they would refuse to go through some of the orifices. So the turbulence conditions and the type of flow that were presented with, they weren't able to negotiate. Again, behaviorally, not ability in terms of how fast they could go. They could actually probably could move through, but behaviorally they wouldn't. So in a further study, somebody further on, Rideout and so on, what they did is they blocked one side alternating. So they blocked this side, so the flow would only go this way. They blocked that side and this side. So now the flow had a longer path, and it was starting to generate more like a streaming flow over these weirs. And sure enough, a lot more American shad moved through. So again, critical how you present the turbulence and the turbulence effects on fish to make it more or less effective. What else can other characteristics of turbulence may also have make a difference on passage as well. So here's some conceptual ideas on different eddies and vortices and their orientation that might make a difference. And conceptually, this is how it was conceptualized by Pavlov and so on. And here's Heinz Tritiko and Cote that actually did a study with a smaller fish and found out that horizontal orientation eddies present more of a problem than vertical ones. And anything close to the fish, in terms of diameter of the eddy, seems to be more problematic for fish. And here's the steep pass that I was talking about. I'd like you to notice that if you look at the side, most of the flow here is vertically oriented. So the eddies that are generated by this type of fishway and many other Deniel types actually is vertically oriented, not horizontally oriented like the pool type and vertical slot type. So fish would have, if we can prove that the fish have more difficulty with our horizontal eddies versus vertical ones, this should be a better way to go. Here's a little bit more on a fishway now, how these some fish, in this case the Iberian barbel, behaved, which sort of gave us another clue about eddies. And this was actually, I got involved with the Portuguese who had an ecohydraulics when we were doing a lot of studies. And Ana Silva was the first student that I dealt with. And when I was examining, I was one of the examiners for her PhD thesis, and this was the last chapter in her thesis. And she could not explain, to my satisfaction at least, why here's a pool and weir, a pool and orifice actually, fishway. We see the orifice here on alternating. So we tested whether alternating or on the same line are preferred or not, and there's a preference there. But more importantly, I would like to concentrate on this. They introduced a small bar on the one halfway through the two weirs. And for whatever reason, small fish were able to navigate this fishway with the bar a lot easier than large fish. So, and remember, large fish have better speeds, swimming speeds, than small fish. So couldn't explain it on fish speeds, right? You had to find something else. So as a postdoc, when she came to Canada, this is the first thing we did. We said, okay, let's analyze the eddies and the circulation patterns within its pool. And here's the pool with the orifice and the bar. And you can see the one on the right, how much different the eddies are in terms of size than the other two. And these eddies turned out to be a lot closer in size to the size of the larger fish. So they were affecting the larger fish a lot more than they were affecting the smaller fish. Again, seemed to indicate that eddies close to the size of the fish are the ones that are problematic for their stability, for their movements. In a further, more recent study, actually in Quebec, with a smaller ecohydraulic flume, it was intended to present baffles to how to design them so fish can get through. And they were tested with rainbow trout, small juvenile rainbow trout. And the difference here was if you test the fish with just a bar here versus a bar and a wedge, you can see the flow patterns would be quite different. And people actually, this research group did a lot more detailed work in terms of not only velocity distributions, but turbulence, kinetic energy, and so on, and looked at the eddies as well. So when there is no wedge here, that's the type of edge, sizes of eddies that you circulate. And I put here the size of that fish. So you can see that this eddy is closer to the size of that fish. But when you put the step in, a very small eddy is generated here. And this did not bother these rainbow trout. They were able to move through. So again, some ideas from that, as well as some values for what turbulent kinetic energy can we do. Now, you can also take all of this kind of information and use a CFD model and see if you can design a fish way better. In this case, we were looking at the vertical slot, and Claudio is part of the RIBES team as well. And we were able to arrive. I just want to highlight a few things. Just this flow that might be more efficient for a lot more species than salmon. Not quite as large as and strong swimmers as salmon. Just under 7%. And I say that because the most recent study we published this year is, can we relate turbulence to anything to do with stressing fish? And yes, we can, it looks like. So this one was done in Iran, actually, on with rainbow trout, and different different hematological and immunological measures were taken, as well as stress measures by taking blood samples and analyzing them, and then exposing these fish to different hydrodynamic conditions, different slopes from 4 to 7 and 10%. And the spacing of these weirs was also changed from 2 between them, relative spacing, 4 and 6. And you can see the overall conclusion was there was a limit for turbulent kinetic energy and turbulence intensity, for that matter, that would not stress these 15-centimeter fish. And it turned out to be around a slope of about 4% was the best condition for them, and the spacing of the weirs of about 6 relative spacing. So again, you can correlate, you can relate eddies, stress, turbulent kinetic energy of flow, and so on, with what happens to fish. And this table just really, we don't have to go through it, just summarizes some of the latest numbers that through most of the studies that I'm familiar with. And some of them are on salmonids, whether they're rainbow trout or juvenile rainbow trout. Some of them are on barbel. And there's one field study here from Norway, actually, on Atlantic salmon smolts going downstream. And again, a lot of these numbers seem to give us a rough idea of what might be suitable for fish or not. One more study from, this is for downstream now, moving fish, in terms of accelerating flows and whether fish actually move through them or avoid them. And what turns out to be is when you present fish for accelerating flows, and that has applications on, helping to bypass fish around dams to go downstream, is fish will fight the acceleration until they're exhausted. So you want some idea of what can, how you can present the acceleration rate so they can actually go with it and move downstream without stressing too much. And over the years, there has been some information on this. And again, you can look at turbulent kinetic energy, Reynolds shear stresses, and so on, and you can come up with some reasonable values. And furthermore, another study we did a while ago here at the University of Manitoba, actually, we started this on the hydrodynamic end. So we did all the hydrodynamics here, and in Portugal, they did all the testing with eel and barbel. And essentially, we were looking, okay, if these fish have to go over spillways, they're a safer way, or is there a way to guide them better over the spillway so they can efficiently move downstream? And we looked at the classical spillway is 90 degrees. But we said, wait, what if you play with it and say, well, what if it was 45 degrees or 30 degrees? Well, it turns out that especially for eel, which are thigmotactic, as we call them, they need to find their way by touching and feeling. We're helped a lot by the 45 or the 30 degree angle spillways compared to the barbel. The barbel was all help, but not as much because they're more of a rheophilic fish. Along those lines, more recently, actually, we are in the middle of analyzing the data on this. Again, at the University of Manitoba, you can see the group down here. The student, Ali, just joined us, I think, for this talk. The idea here is to collect as much data in a very detailed way, because now we have access to a stereoscopic particle image velocimetry, and we can even have 3D if we want to get out of this, and analyze the data, have enough hydrodynamic data to analyze them for the different shapes of the spillways we're talking about, the 90-degree, the 45-degree, and the 30-degree. And then we can actually see if we can use this as a basis and present test fish with different species in different situations. And one item I wanted to highlight is that it turns out from literature that this idea of 1 meter per second per meter distance sort of spatial acceleration seems to be a good indicator, at least for juvenile fish, might be a good critical value to help them go down or not, sort of a dividing line. So we're looking for people that, partners that are interested in testing, utilizing this data set once we analyze it, and testing it with different species. And you can appreciate that you can use salmonids, you can use cyprinids, you can use eel, you can use sturgeon. If people have the ability to do this in the lab or in the field, we're interested to partner with them to further these studies and actually test some of these ideas with fish. So we would welcome that. Now, bottom line, can we have effective fishways? Because I mean, a lot of times that's what we're doing it for. And yes, when it comes to salmon, actually, we have some very efficient fishways if they're designed properly and operated properly and so on. And the best example I can show you is this one on the Bonneville Dam, actually on the Fraser River in Canada. The vertical slot is one of the most efficient ones as well. They have a long history of operating that one as well. So you can see you can reach 95% levels of passage. And even when you go over several dams, you still have a high percentage of each dam, of course, takes its toll, but you can still have a high percentage of fish. But that's salmon. These same fishways would not pass sturgeon because they're too big and they wouldn't even fit through orifices because they prefer to move through, let's say, through the bottom. So they were designed for salmon, so they operate very well for salmon, but not for sturgeon. Or Pacific lamprey, a different mode of operation, a different mode of swimming. So they have started actually developing special fishways for Pacific lamprey. We have special fishways adapted for eel and still working for sturgeon and so on. So one size doesn't fit everybody, and we need to take into account their abilities, not only their abilities, but even more so their behavior, because a lot of times fish are capable of doing something, but the turbulence and the flow patterns we show them, we present them, are not suitable for their behavior. Do we have any hope for non-salmonids though? It looks like things are improving, and this study in Spain put together everything mostly from Spanish fishways, which were done much more recently. They were built after 2000. Before 2000, actually, most fishways, they were concentrated on salmon and they were copying salmon fishways. And it's not surprising that there are a lot of other species, whether we found them in Japan or Australia or other countries, were not very suitable for the species at hand. But once people are starting to design with more of their species at hand, things are improving in terms of effectiveness. And again, we can be overconfident or not confident at all. That neither one is true, actually. And a lot of times there's a lot of unknowns that we are still trying to come to grips with. So let's say in this sockeye salmon population of the Fraser River, where this vertical slot fishway was first developed in the Hell's Gate, it was developed to overcome that big landslide, right, that I was talking about. And in 2010, the population was dropping dramatically before that, but in 2010, it increased dramatically again. And it reached the levels about a century ago, before that landslide made life very difficult for them. So in the end, and I like this cartoon from the Winnipeg Free Press, actually back in 2010 when this was in the news, we have to think like a fish, right? To start to see what they need. But we can do our best. Let's remember, though, that in the end, fish have the last word. We still need to know a lot more. So in this area, and we only talked about fish in turbulent flow and so on, but in a more general ecohydraulics area, we cover a lot more than that, and trying to integrate interdisciplinary knowledge, which can lead actually to innovation and practical applications to a more sustainable and ecologically sensible water infrastructure that we all would like to see. There are still tremendous challenges and opportunities, and for pioneering research in these areas, so we can go towards more knowledge-based applications in the ecohydraulic, what I call the ecohydraulic trilogy, because a lot of times we talk about fish passage, and beyond fish passage, other organisms actually in the water that are also need to move up. Environmental flows and habitat restoration are also there. And climate change and nature-based solutions are big in these are in our times too. But to me, the best solutions are found by integrating all these aspects together at the beginning of a project when we're considering a new project, or integrating when we're trying to modify a project. And finally, I want to emphasize that we're always learning. I mean, go back to the Solon the Athenian, Girasko dai poladi daskomenos, which means I grow older, ever ready to be educated on many things. So yeah, since Leonardo first observed some eddies and vortices and so on, we've learned quite a bit, but we still have a long way to go. And I'm glad to see so many biologists and engineers getting involved in this interdisciplinary area. So I'm sure we're in good hands to get much better understanding of all these aspects. Thank you very much, and sorry for going so long.